Just to summarize what we have so far, I've got a table here with different options for what you may see with the forcing function. So we talked about the three cases where undetermined coefficients comes in handy. It's when you have an exponential function, like this first example, or a cosine or sine function, or both, or you have a polynomial. So those are the three cases where this is useful. And you've got a summary here of what the form of your yp would look like. So for an exponential one, notice the coefficient in the exponent stays the same, but the coefficient in front of the exponent is what we build with this undetermined coefficient. So that's the piece that you use. Then for whether you have just cosine or just sine or both, you use this full form where you have a term for cosine and sine, and then you have coefficients for each of them. Now, by the way, we'll talk in a minute about what to do if you have more than one of these, but if, for instance, I had cosine of 3t and sine of 2t, those would count as two different pieces. So we would need one of these with 3t and one of them with 2t, one for each of those pieces. So we'll talk about that a little more, but just keep that in mind that when we talk about both added together here, we mean specifically if they have the same coefficient of t inside the trig function. So watch out for that. And then lastly, if there's an nth degree polynomial, we talked about how you need an nth degree polynomial. And again, say this were like t to the third, you would need every term from t to the third all the way down to a constant. So you need to include all those values. Even if some of these might be 0 in the end, you can't assume that from the beginning. You have to start by accounting for the possibility that all of them are non-zero and then work them out. So that's the individual pieces. Now we can deal with any one of these three in isolation. But the question now is, what if we have more than one piece? What if f of t is a combination of them? So when I say a combination, there's two different ways we could combine these. One using summation, adding pieces together, and the other multiplying pieces together. It turns out these are pretty simple if you're going to combine them. Sums are especially easy. So we're going to use, again, the idea of superposition. And again, in brief, the idea of a superposition is that if you know two individual solutions, the full solution will be the sum of them. So the idea here basically boils down to create a term for each piece. So for example, let's say we had something like this one. The left-hand side is not as important. The important part is this right-hand side. We can keep going and add a couple extra terms just to show you different variations. So each one of these pieces will get its own piece in yp. Now again, notice we talked about this a second ago, but these sines and cosines are not the same, since it's sine of 3t and cosine of 6t, not the same form. So we're going to build one of these pieces for each of them in our final yp. So going through this one piece at a time, the 6t squared, we need a second order polynomial. So we would have at squared plus bt plus c. Then for the sine of 3t, we would need sine of 3t and cosine of 3t. And the order doesn't matter. Then for the 9, we would need, in theory, another constant. So we could put plus f. Now, this isn't actually necessary, because what you could do is you could sort of lump this in with a 6t squared and assume that the c is going to take care of that plus 9. So we don't really need the f as the extra piece, just to save ourselves a little bit of effort. but then the e to the 4t is going to get a term, and then the cosine of 6t will get a cosine and a sine term. So it's kind of an extreme example with a bunch of options, just to kind of show you all the different pieces that you might have to include. Now this one would be really long and tedious with all these different coefficients, so we won't complete the problem, but that's how you would set up your particular solution. So sums are really straightforward. All you have to do is create one piece for each one, and then add together all of those to make the full particular solution. Now again, you might find cases where some of these can be lumped together into one piece, or if these were both 3t, you could lump those together and so on. So, take advantage of things like that to simplify your work, but in general, the idea with the sum is just to add together all the different pieces. Now the question is, what about a product? And it turns out that a product is really similarly simple, so it's not really any more complicated. So we're going to use the product of the individual pieces. So in the same way that if you have a sum, you can pick each piece individually and add them together, it turns out with a product you can do the same thing. Now, we're going to simplify this in a second. And it may not look like simplifying at the time, but you'll see how we get to the end of this, how we end up with a simpler idea than the full product of all of them. So let me show you an example of what I mean by that. Say, for example, we have something like this. Again, the left-hand side is not what we're focusing on here. Let's say on the right-hand side we have 5t squared times e to the t. The two pieces we have are a second-degree polynomial and an exponential. So we're going to start with those two pieces. The first piece will have at squared plus bt plus c. And then the exponential will get its own piece. We have the product of those two. Now there's a problem here that may not be apparent until you start working out the problem. And we're not going to complete the whole example. If you'd like to try it, you can, but you'll notice that you're going to run into an issue. The issue you're going to run into is that we have too many constants over here. Notice we have an a, a b, a c, and a d. But if you work this out, you're only going to get 3 equations. So we'll have 3 equations and 4 unknowns. And so the problem breaks down. So what's the solution to this? It turns out the solution is pretty simple. All you do is distribute this out. In other words, let's start multiplying this out. This would be AD times t squared. If we move the d into the first set of parentheses, plus BD t plus CD times e to the t. In other words, this d is really superfluous because if we distribute it through, we can just relabel all of these A and B and C. And so we'll summarize this in a minute, but it turns out that the coefficients A, B, and C are enough to make this situation general enough, because if we include one for the exponential, that can just be distributed through and relabel them accordingly. So in other words, this can sort of take on the work of building the coefficients, and then the exponential doesn't need one in that sense. So we'll summarize this a little later on so you can see it maybe more clearly. But for now, this is the reason why that happens, that we can relabel these. And the coefficient on e to the t was unnecessary. So instead we could have just selected yp to be at squared plus bt plus c times e to the t.